Hello everyone, my name is Milan Skala and today I'm going to talk about the RISC-V configurability in compliance test framework. So at first I'm going to say something about the achievements and activities of Codasip in compliance task group. Then I will move to the core of this presentation, which is the Codasip compliance framework which we have designed. I will show you the framework scheme, then I will move to the automatic plugin generation and custom model integration process. And at last, I will show you some examples of framework reporting and automatic test selection. So Codasip has joined the compliance task group in 2017. And since then, we are trying to do our best to make the compliance process as simple as possible for the users and also to keep the compliance test suite maintainable. We have initialized the RISC-V compliance test process definition, and we are the first who implemented the RV32i tests, which are used in the current test suite. More lately, we have made a proposal of test format specification, and our latest work is on the compliance framework implementation, which I am going to talk about more lately. So, in the proposal of the compliance test format, we have tried to unify the directory structure and file naming convention of the sources for the tests. So, adding a new test to the test suite is pretty straightforward process. We have also defined the test structure, which includes unified user-defined macros for test sections and common header files which are used among all the tests. We have also defined the signature format specification, and it, of course, includes glossary definition for some ambitious words. So now I'm getting to the core of this presentation, and that is Codasip Compliance Framework. It's a high-level framework for compliance testing of RISC-V model, and it is able to, it supports any implementation of the RISC-V processor, including ISA simulators, RTL descriptions, and so on. It's also easily extensible with new tests and models, thanks to the proposal we made for the specification which I have talked about earlier. It also automatically selects the test based on the model configuration, meaning that the tests which should not be executed for a given configuration are not even executed and they are skipped. So it saves some time. We also include a support of custom toolchain for test compilation, so you can use your own toolchain and not only the official RISC-V GCC compiler. The framework has simple and intuitive user interface and user-friendly reporting system. So we chose Python 3 as the implementing technology for the framework because of its high-level OOP description, fast code implementation, and easy readability. Python's strong side is the readability, so anyone who never saw Python before can easily read the code, and he doesn't have to study the whole framework. We use the PyTest package, which is a package for automated testing, which supports full customization of the testing process. PyTest divides the testing process into 3 phases. The first phase is collection phase, where PyTest gathers all the available tests and eventually filters some of them. Then the second phase is execution phase, where the tests are executed, and the last phase is reporting. Each of these phases is fully customizable, and the framework uses that feature. PyTest also allows implementing custom plugins and their easy integration. We use also XDis plugin, which is fully compatible with the PyTest for parallel test execution. So here's the scheme of the framework. You can see it has only one input, which is the user plugin. The user plugin here represents the tested model. So it stores its configuration and behavior and its general interface to the model. The plugin has 3 components. The first component is compiler wrapper. As I talked about earlier, it serves for the source compilation. The next component is abstract model. This is the most important component as it contains the implementation of the model and it stores its configuration. The last component is the environment. The environment is just a set of supportive files, including some header files, linker scripts, your custom scripts which you want to execute during the compliance testing process. So when the framework loads the user plugin, it searches for all compliance tests. Then, based on the user model's configuration, the framework selects the subset of these tests, so only the relevant ones are executed. The next step is the subset of tests is compiled and executed on user model and on reference model. For reference model, we currently use Spike, but we are waiting for formal group to finish their formal model, so we can use that. The formal model should be more powerful than Spike. After the tests are executed and finished, the framework generates the HTML and XML report. So here's once more the plugin structure. It has three components: abstract model, compiler wrapper, and environment. Abstract model implements the functional behavior of the tested model, and it's also responsible for signature extraction. The compiler wrapper, it's responsible for correct assembly compilation, and user has to implement that only when he's not using the RISC-V GCC. If he's using his own toolchain, he has to implement the compiler wrapper because it's not implemented in the framework. The last component is environment, and it contains the files for correct compilation process and some other custom scripts and whatever the user needs. So here is next part of the framework. It implements a plugin generator for easier model integration. It's implemented as GUI, a wizard-like GUI. So it's a pretty straightforward process to generate the plugin. At first, the user selects the ISA of his model, then he selects the extensions he supports and modes. The next step is he defines his memory map, and if he supports interrupts, what kind of interrupts he supports, control and state registers definition. And the last step is the target selection. You can think the target as some template for a specific RISC-V model. So here are the steps for the custom model integration. The first step is that you generate a plugin using the generator. This creates the directory structure and the default implementations of all the components I've talked about earlier. The next step is you define the macros for custom processor model. These macros contain reset vector address, processor initialization, and so on. Next, you have to implement a custom compiler wrapper if you need it. If you don't use your custom toolchain, then the RISC-V GCC wrapper is used and it's implemented in the framework itself, so you don't have to write a single line for that. And the last step is to implement the abstract model behavior. This includes specification of arguments and execution of the RISC-V model. And the last step is to execute the test suite and wait for the results, which are given by the framework. Here is an example of framework reporting. It generates a report in two formats. The first format is XML report for machine post-processing, in case you want to store the results in database or whatever. And the next format is HTML report for user friendliness, where you can choose or filter the test by the result. The result is passed, skipped, or failed. And in this example, you can see that 79 tests has passed and 105 has been skipped because the model did not match the configuration which was required for the test. If the test is skipped, you can see the reason why it has been skipped. In this case, it's because the tests were meant to be run on RV64i, but the tested model was RV32i. So when you execute the framework, you can also get a console report. You can see in the header the information the framework is using, including the ISA tested, ISA of the model, toolchain, if there is any. By default, it's the RISC-V GCC, the path to the plugin, the path to the model itself, and so on. You can see how many tests has been collected. In this case, it's 184. Then follows the execution phase of the framework. So the tests are executed both on reference and user models. Next to the name of the test, you can see its result. S means for skipped test, so it hasn't been executed, and dot means for passed. There are other letters in case of failure or another errors. So as the last step, you can see the framework has generated the reports in a specific path. And as the last section, you can see the tested configuration and some more detailed information about the tests. So now I'm going to talk a little bit about the automatic test selection and how that one works. The framework selects and executes only tests that should pass on the specific RISC-V configuration. It uses PyTest markers, which is an easy way to filter the tests. The markers can be parameterized, and they are extensible for any RISC-V feature or configuration option. So here's the example of the test in the framework. On the top, you can see the decorators, so-called markers, and they specify where the framework searches for the tests, and some pattern for the tests. We can see that it finds only assembly files. And next marker is it filters the test by the model configuration. So these tests should be executed only on RV32i ISA and models with an extension. In the test body, you can see that the test is compiled for both reference and user models. Then it's executed on both models, and then signatures are compared on match. So here is the list of currently supported targets. We have successfully integrated Codasip SDK with Codasip Simulator, RISC-V GCC with Codasip Simulator, RISC-V GCC with RISC-V OVP SIM by Imperas, RISC-V Verilator, and Codasip SDK with Codasip RTL, which is proprietary, so we did not include the target in the GUI. So that's all from me.